Our lecture is focusing on the time properties of simple dynamical systems, followed by more complicated such dynamical systems. So, after doing this time domain we will also discuss frequency domain properties of the same dynamical systems. So what do we mean? Well, we mean that any of the dynamical systems that we're looking at has a behavior, meaning that its output follows a certain trajectory for a given input. For example, when the input is a step, then the output may look like this, or it may look like that, etc., etc. And the fact is that we have seen already some examples of that, and what we have done is use, for example, the command csim to obtain the response curves. Now, what we want to do is look more in depth at what the response looks like for first order systems, second order systems, and then arbitrary order. Often we will see that we can think of even arbitrary systems as first and second order systems. However, for now, we will say that they are very different, even though engineering insight will eventually lead us to studying mostly these kind of responses. So, to begin with, we will talk about first order systems. First order systems, so I said first order systems, they look like follows. d dt of x is equal to a times x plus b times u, where x, u are numbers. To be more precise, scalar functions. And we have already seen what these systems look like. For example, if I have a certain condition x of 0 is equal to x0 and u is equal to 0, then we know that x of t will be equal to e to the at times x0. And the response of the system is summarized by this quantity. Now, what does this response look like? Well, it looks like a decaying exponential. If x0 is here and 0 is there, notice that x0 could also be negative. Okay, then the response of the system will look like this. Okay, it doesn't go exactly under 0, but my pen did. Okay, it remains positive at all times if the initial condition is positive, or negative at all times if the initial condition is negative. Okay, now let's look at some properties. Okay, one of them has to do with the tangent. Okay, and indeed, when we look at this thing, okay, we can linearize and obtain that x of t is equal to x0 times 1 e to the at and e to the at we can approximate as 1 plus a times t. So x of t can be approximated as x0 times 1 plus a t. Now, so this thing is that expression, okay, x0 times 1 plus at. Now, where does it cross the 0 axis? It crosses the 0 axis at the location t such that x0 times 1 plus at is equal to 0. We assume, of course, that a is negative, otherwise we have a growing exponential, which is not of much interest to us. And what we obtain is that t must be equal to minus 1 over a. Now, interestingly enough, what we can do is look at the value of the response itself at this point, which is minus 1 over a. And we see that the value here will be x of minus 1 over a is equal to e to the minus 1 times x0, which is about x0 divided by 2.7. Okay? So, we might be interested in then studying step responses. So, for that, we will assume that x0 is equal to 0, and we will select another picture, okay, whereby we again pick d dt of x equals ax plus bu. We set x of 0 is equal to 0, and as I said, we study the step response. The step response will be satisfying d dt of x is equal to ax plus b with x of 0 is equal to 0. Now, to solve this equation, what we can do is take the variation of the constant and say that the solution will look like x of t is equal to e to the at times g of t. Now when we plug this in here, we obtain that d dt of x is equal to e to the at times g of t plus e to the at g prime of t. So that since d dt of x is equal to ax plus bu, this must be equal to e to the at g of t plus b. Okay, and again we call that variation of the constant. That's the method, okay, which amounts to postulating x of t looks like this. Crossing out the two terms, we get that g prime of t must be equal to b times e to the minus at, or in other terms, g must be equal to g0 minus 1 over a times b e to the minus at. Now, since we know that x of t must be 0 at t is equal to 0, what we conclude is that g0 must be equal to 1 over a b, such that x of t now looks like 1 over a times b times 1 minus e to the minus at. Okay, so what have we got here? We have a description of the solution of the response of the system. Now, what do we find? We find that so g of t is equal to g0 times this, okay, and so x of t is equal to e to the at times g. So I multiply this by e to the at, okay, and I can therefore rewrite this as b over a times e to the minus at minus 1, which is a whole proper expression. And what we can say is that this kind of response looks like this. Okay. Let's change this. And we just have time t here. We have minus b over a here. And what we have is that we have, instead of a decaying stable exponential, we have an increasing stable exponential, which plateaus as minus b over a. This exponential is very much of the same shape, but flipped over along the t-axis compared with the previous thing, which was the initial condition response. Now, if we look at the impulse response, it's about the same, okay? The effect of an impulse is to look at the response of the system ddt of x when x ddt of x is equal to ax plus b times delta of t. Okay. Now, in this case, the effect of delta is to reset the system at b. Okay. So, if I clean up a little bit what I have, okay, and I look at again the impulse response. Okay, so I cross the step response. I only show the impulse response. Again, we said d dt of x is equal to ax plus b delta of t. Okay, and we know that this is equivalent to saying that we're looking at the system d dt of x is equal to a times x with x of 0 is equal to b. Okay, and that's because of the fact that the effect of an impulse like delta is to instantaneously transfer the state of the system from 0 to b. Of course, we assume here x of 0 is equal to 0. Okay, so the impulse response will look very much like, again, that decaying exponential we have already seen, which looks like this, okay, and remains positive all the time. But we have already looked at it. Okay, so now what we're going to do is talk a little bit about more interesting systems, okay? And probably the more interesting systems is what we call second-order systems, okay? Second-order systems are very interesting because although they may look simple, we can approximate many systems as second-order systems. And so that's the power that these systems offer to us. Okay. Now, a second-order system is typically of the kind d dt. It's typically of the kind x double dot plus bx dot plus cx is equal to u. Okay, we have seen many systems that do that. Mass spring systems, also pendulums. I mean, all these like satisfy the same equation, or RLC circuits. Okay. So the question is, what is the time response of such systems? And the answer really depends a lot on the parameter B and C. Okay. The best way maybe to analyze these systems is to go in the transfer function world. And then we obtain that x hat over u hat is equal to 1 over s squared plus bs plus c. Okay. Now, here's what happens. Okay. When c goes up, we have faster oscillations. when B, which we assume is always greater than 0, so is C, okay, when B goes down to 0, we have more sustained oscillations. Okay, so now let's look a little bit more at the details of this thing. For that purpose, we're going to start Scilab and look at what Scilab has to tell us about such systems. For that, we're going to talk about a few interesting experiments. Okay, the first is we're going to define a variable s like this. Okay, and then we will define our system as 1 divided by s squared. So we're going to define a and b, okay, or b and c rather. We're going to define the values of b. This is 0.01, okay, and c, which will go and define as 1 for now. Okay. Now, what we do is we define the system as 1 over s squared plus bs, b times s, sorry, plus c. Okay. So we have that, given our transfer function like this, and we would like to simulate that system. Okay. So for that, we will discuss we need to use the csim function, which I keep forgetting about. Okay. So csim will be equal to what? How do we use it with transfer functions? The help window will come out very soon, and says that we can write we can use it as okay, so we will use csim, okay, and what we will do is we'll make the following command. Okay, we'll play csim, but we will say that we want the step response of the transfer function. Okay, so we will say they want the step response over the interval 0, 0.05, and then 9. Okay, so over 9 seconds, and then we will say that it's for the system named sys, and we set no initial conditions because initial conditions make no sense in transfer function. And we are told that t is equal to 0. Okay, so we'll do it again. And why don't I define t first? So t is equal to 0, 0.05, 9. Okay, and now I can restart my simulation, and I will say that this is t. Okay. All right. So we have a continuous time simulation. A window comes up, and the response of the system comes up. And what you see is that the response of the system is indeed oscillatory, very oscillatory. Okay. So what I would like to do now is do an experiment by looking at what happens if I change the oscillation. Okay, I change B. Okay, so I'm going to say B, instead of being 0.01, I will say 0.1. Okay, and I will define my transfer function as I have done before. Let's see what happens. Okay. Now, on the same plot, what we will have is that now the system will look a little bit different. Okay, the system doesn't start as high, doesn't go as low, and then seems to be settling up a little better. Okay, now this is not necessarily a very appealing curve, and besides, the colors are not very nice. So relying again on this, I will look at how I can specify a color. And so let's see that. Oh, so we need to look at plot 2D. Okay, so plot 2D. So we can use. Okay, so we can use a different color. How do we do that? Let's see. Let's see what color says. Okay. So color says. Okay, so that's a color. Okay, so let's look at color management. Well, we will keep doing our experiments in black and white for now. So what I propose is that we're going to use instead, we're going to now improve B, and instead of making it 0.1, we're going to make it 1. Okay, and see what happens. We define our new system in such a way that now, when I do the same plot as before, okay, here's what the system looks like. Okay, instead of oscillating violently like it did before, it now gets towards 1 rather quickly. Now you notice that the oscillation frequency doesn't change very much, but on the other hand, the response is much smoother. Okay, and that smoother response, together with a faster convergence to 1, indicates, in general, probably a more desirable behavior. Okay. Now let's look at. We can do some further experiments. Okay. For example, if we pick B is equal to 2. Okay. Then what we'll see is that the behavior of the system will be slightly different, in the sense that the system now does not overshoot at all. It just increases, and then settles at the at some value here, which is close to 1. Okay, that system oscillates. That system oscillates slightly. That system does not oscillate. If you were to look at somewhere in between 1 and 2, you would see that the system still oscillates, whereas and therefore the only value above which for B above which the system does not oscillate is B is equal to 2. Okay, for that reason, this is named a critically damped systems. Okay. Now let's see what happens to A. So if we write C is equal to, instead of 1, let's call it 2. Okay, and let's see what happens with that. Okay, so again, we define our system like this. Okay, and we do the simulation. Now, normally, two things should be happening. Okay, so first of all, the system is still well done, but it goes down to 0.5 instead of 0.1 of 1. Sorry. Okay, and that's normal because the steady state value here for an impulse for a step would be 0.5. Okay, if I increase C, okay, what we will see is two things. Okay, first of all, that the oscillation goes faster, and second, that the steady state value goes down. Okay, so let's see that. Let me code the figure, and this is exactly what we see. Now the system goes to 0.3 instead of probably 0.33. Okay, and really remains quite happy there. In order to get something more significant or more interesting, we need to scale things by C here. Okay, because if we do this, okay, we know that the step response is going to be of the same magnitude as what we had before. And sure enough, this is the step response here. Okay, now if I increase C even more, okay, and I say that C is now equal to 20, okay, here's what will happen. Okay, we have scaled our system in such a way that the simulation of the system now returns something like this. Okay, the system oscillates faster, and it responds otherwise pretty much like its neighbor when C was lower. Okay, so let me clean that picture and do a few more experiments. Okay, what we're going to do is we're first going to run C here, okay, and see what happens for a fixed B for different values of C. Okay, so we're going to pick like a value of C, say, which is equal to 0.5, okay, and see what happens. Okay, so the response of the system will surely look like, well, very sluggish. Okay, but going otherwise towards 1. Okay, so what happens if I now do C is equal to 1? Okay, and I introduce my transfer function like this, and I look at its step. Okay, well, here's what we see. Okay, what we see is that the response of the system becomes faster, and still goes towards 1. Okay, what if I go even faster? Okay, so I write that C now is equal to 2. Okay, and I do the same experiment. Okay, then what I will get is that the response of the system will now look like this. Okay, so it develops some overshoot. It is faster. Okay, but it overshoots in such a way that if I now go towards C even faster, okay, so I say 10, okay, I will obtain the following response. Okay, so we have it here, and what we have is this response. Okay, as we go faster and faster, what we obtain is faster and faster response. And I don't know if you noticed, but they look like there is an envelope to these responses. Okay, and they look like this. Okay, now these guys escape the envelope, but then eventually they look like they leave all in the same envelope. In fact, look at how this guy just touches here this oscillation just touches that one over here, it really feels like, you know, like an envelope. Now, we will discuss this in more rigorous terms soon, but for now, I just want you to make observations. We did C is equal to 20, so we're going to do C is equal to 100. Okay, so it's going to be a very high oscillation, and we're going to see what it gives. Okay, so the oscillation now looks like a very fast oscillation. Okay, and the system doesn't, you know, dumps out, sure, but it dumps out at the same speed as it used to, but it oscillates. It has more room to oscillate a lot before it dumps out. Okay, so to look at the format and to understand more fundamentally what goes on here, okay, what we need is to study this guy in more detail. Okay, and so this is exactly what we're going to do. Okay, what we're going to do is look at this transfer function. Now, as you noticed, okay, there is a lot of value into scaling the system in such a way that the transfer function looks like C over S squared plus BS plus C. Okay, so that the step response always goes to 1. Then another thing that we can do is write that since C is sort of a natural frequency squared up, we can write that C is equal to omega 0 squared. Okay, this is always possible since C is greater than or equal to 0. And then the transfer function therefore looks like omega 0 squared divided by S squared plus BS plus omega 0 squared. Okay, now what we're going to do is we're going to introduce another notation for B. Okay, we're going to say that B is equal to what's called 2 times zeta omega 0. Now this is always possible because B is positive, omega 0 is given, and zeta can be chosen to be B over 2 times omega 0. Now this may look artificial, but I will show you why not. Okay, as a result of choosing that notation, we get that the transfer function now looks like omega 0 squared divided by S squared plus 2 zeta omega 0 squared plus, 2 zeta omega 0 plus omega 0 squared. Okay, now why is that a useful thing? It's because as zeta varies from 0 to 1, okay, we get that the response of the system goes from pure oscillatory to critically damped. Okay, what we have seen is this response where the system actually goes up to 1 but never exceeds 1. Okay, for that purpose, zeta is named the damping ratio. Okay, now let's look at the effect of changing of using this notation zeta omega 0 as opposed to B and C. Okay, so for that I reopen the Scilab. Okay, I close this picture and I reopen the command window. Okay, so what I'm going to do is I'm going to choose so instead of B and C, I will choose like zeta, which I would say, for example, is equal to 0.1, and omega 0 is equal to 10. I will then define my system as system is equal to omega 0. It's kind of painful the first time, but it's okay. 2 times zeta, zeta times omega 0 times s plus omega 0 squared. Boom. Okay. Now let's look at the response of that system. So the response of that system doesn't look much different. Okay. However, one interesting thing happens if I change zeta without changing omega 0. Okay. So for example, I'm going to do zeta is equal to 1. Okay. And I plot the same response of the system. When I plot the response of the system, what I get is that, I forgot to update my system, sorry. Okay, so we're going to do that now. And the response of the system now looks like this. Okay. If I, and again, this is a critically damped thing. Okay. If I pick zeta to be equal to 0.5, okay, and I plot the response of the system, again, as we have seen before, yes, we generate a little bit of oscillation. Now the nice thing is that as we change zeta, okay, what's called the natural frequency of the system doesn't change much, okay, and so we can plot on the same plot the response for different values of theta, and we can compare them together, okay. And among other things, you know, we see that sort of the response, the time response, doesn't change much. Now, let me look at the effect of changing omega 0 instead of changing C. Okay, I think the effect will be pretty clear quickly. So I erase this. Okay, I define my system, and now I don't change zeta. I just change omega 0. So let me do this first simulation, which is the same as what we had before. Okay, and we see the system response like this. Okay, now what is the effect if I change omega 0 and I write omega 0 is equal to, instead of 10, we make it 2. Okay, and we again simulate the system. Okay, so we do plot 2D. We first need to define the system, and then we do the plot 2D thing. Okay, as we call upon this, here's what happens. You see, the time it takes for the response to evolve is shorter because we have not as high oscillation. However, the shape of the response is the same up to a scaling in time. Okay, so what that means is that, for example, if we are to shape a response in terms of how fast it rises, but we don't want to change the overall shape of the response in terms of overshoot. The overshoot is the distance between here and there. It's expressed as a percentage of 1. Okay, then we can simply change omega, okay, and then be content with that. Okay, we can change omega, and we can obtain a change in the function in the response without changing the general shape of the response. Okay. Now, if you remember, when we did the same things with B and C, okay, and we changed C, not only did the response go faster, but also as C went up, it became more oscillatory. Okay, and that is sort of a bad parameterization. Okay, because too many things change as we change one variable. Okay, so we're gonna use this notation. Now, of course, we can go from one to the other without any problem, since we can define always C is equal to omega 0 squared, and B is equal to 2 zeta omega 0. Okay, so given zeta and omega 0, we can find B and C, or given B and C, we can find zeta and omega 0. Okay, very easy. All right. Now, we will look at the kind of response we get. So for that, I will look at the following. Okay. First, we will go for a more complete description of the transfer function. Okay. And that transfer function will pick, as I said, as omega 0 squared divided by s squared plus 2 zeta omega 0 s plus omega 0 squared. Good. Now, let's look at the roots, okay? So to get the roots, we first compute the reduced discriminant, okay? And we notice that the reduced discriminant is going to be zeta squared omega 0 squared minus omega 0 squared. What does that mean? That means that another way for writing it is that delta is equal to omega 0 squared times zeta squared minus 1. So when zeta is greater than 1, then we have pure real modes, okay, and or pure real roots to the characteristic polynomial here, okay. And in that case, that means that we can rewrite this guy as a over s plus r1 plus b over s plus r2, and r1, r2 are real and negative. Okay. Now, if zeta is less than 1, then we have complex conjugate roots, okay, which means that instead of writing s squared plus 2 zeta omega 0 s plus omega 0 squared, okay, is equal, we're going to write it as s plus c1 times s plus c2, where c1 is equal to c2 bar, and there will be so therefore complex rules, okay, complex conjugate rules. Whereas here we write the same thing as s plus r1 times s plus r2, okay, and r1 and r2 are real. So the value of zeta relative to 1 is very important, Okay, we're going to begin with zeta greater than 1, and then we'll end with zeta less than 1, with, of course, the intermediate case zeta is equal to 1. For that, let's first pick the case, the extreme case, zeta is equal to 1. In this case, our transfer function will be omega 0 squared divided by 1 plus, s squared plus 2 omega 0 s plus omega 0 squared. Okay, and what I can do is rewrite it as 1 over s divided by omega 0 squared plus 2 times s over omega 0 plus 1. Okay, and we can define the reduced variable, which we call s hat, which we call it as s over omega 0. Okay, under these conditions, this transfer function can be looked at as 1 over s hat plus 1 squared. Now, if we want to compute the step response of this, how do we do that? There are several ways to do that, but one of them is, of course, to take the Laplace transform inverse of 1 over s times 1 over s plus 1 squared. Okay. Now, what does this look like? There are several ways we can do that. Okay. One of them being to remember what's written in the book, okay, and the other being to sort of go with our own hands. And I usually recommend that you just go with your own hands. Okay, so what I'm going to do is I'm going to forget about all this and then rewrite this story about computing the inverse Laplace transform of 1 over s times 1 over s plus 1 squared. The first step is to rewrite this as a over s plus b over s plus 1 squared. I think that should be good enough. Okay, now a over s, so if this is true, then we should have like a times s plus 1 squared plus b times s. We're going to say plus, so we're going to say b times s plus c here plus d over s plus 1. I think this is better. Okay, and the reason is because otherwise I don't have enough parameters to play with in order to equate this to the 1 over s times 1 over s plus 1 squared. Okay, so my apologies for this. And so we do this thing first where we identify this guy with this guy. So this is not really the inverse Laplace transform, but just the transformation of this guy via a partial fraction expansion. And we will now obtain that a times, so the numerator will be looking like a times s plus 1 squared plus, and then we're going to have bs plus c times s, okay, and then plus d times s plus 1 must be equal to 1. Okay. So now we equate terms. We see that the S squared term looks like A plus B. Okay, the S terms look like 2A plus C, and then the constant term look like A plus D. Okay, so we must have that this guy is equal to 1, this guy must be equal to 0, this one must be equal to 0. Okay, all right. So given this, and rewriting D a little more cleanly, by the way, I forgot something here, 2A plus C plus D. Okay, I think now we're better. Now, so we get that D is equal to minus A, which we can plug in here. Okay, and we obtain that 2A minus A plus C must be equal to 0. Now here we must have A plus B is equal to 0, so we get that B is equal to minus A. Okay. So let's see how this goes. So here we have 2A minus A, so we need to get A plus C is equal to 0, because 2A plus C minus D minus A must be equal to 0. Okay, so we get that A plus C is equal to 0. Okay, and we get that D is equal to minus A and B is equal to minus A. All right, so what we can do is pick, sorry, D is not minus A. Oh, let me restart this. This is incorrect. This is very incorrect. Okay. So I restart. From this we get that D is equal to 1 minus A. Okay. From here we get that B is equal to minus A. Now we can plug this into the middle, and we get that 2A plus C plus 1 minus A is equal to 0. Or in other terms, A plus C is equal to minus 1. Okay, so we have one relationship here, we have another one here, and we have another one there. Okay, so this is an underdetermined or overdetermined thing, and so what we're going to do is we're going to call, it's underdetermined, meaning that we have too many parameters. So what we're going to do is we're going to decide arbitrarily that A is equal to 0. In which case, what we will obtain is that B is equal to 0, C is equal to minus 1, and D is equal to 1. In other terms, the partial fraction expansion looks like, no, it doesn't work. It doesn't work because then we could say this is equal to A over S, which is incorrect. 0 over S, this cannot be true. Okay, so let's restart this. And let's restart something. So we're going to say, we're going to try something else. Okay. So let's first check that everything we did is correct. So this is A times S plus 1. This is BS plus C times S, yes. And this term, when we reduce to the same denominator, is D times S plus 1 times, aha, we made a mistake here. Is it times S? Okay, now, if I do this, okay, my equations still look like this here. Here, they are still correct, but here we miss a d. Okay, so we miss a d here because there's an s squared term in d. Here we have a d, and then here we just have an a. Now this is very different. Okay, based on that, we can first of all say that what I said before is incorrect. Okay, so for example, what we can do is that all this needs to be erased. And so the next thing is that we're going to discover that a must be equal to 1. Now 2a plus c plus d must be 0. Okay, so we're going to say 2 plus c plus d must be equal to 0. And then from here we need to say that 1 plus b plus d is equal to 0. Okay, so what we could do is choose, given that a must be equal to 1, we have too many determinants here, so we can choose d is equal to 0, for example. In which case we get c is equal to 2 and b is equal to minus 1, okay, and c is equal to minus 2. So 1 over s times 1 over s plus 1 squared is now equal to 1 over s minus s plus 2 divided by s plus 1 squared. And now, equivalently, we can write that this as 1 over s minus 1 over s plus 1, and then there remains minus 1 over s plus 1 squared. Okay, so given that we have done finally these computations, we are in a position where we can now discuss the time response here. Okay, so the time response of this looks like what follows. Okay, so the inverse Laplace transform of 1 over s is a step. Okay, which I call also 1 indicator of t greater than 0. Now 1 over s plus 1 is 1 over s plus 1 will become something like minus e to the minus t. Okay, minus 1 over s plus 1, its inverse transform is minus e to the minus t. Now, what is minus 1 over s plus 1 squared? Okay, well, this requires a little bit of care, and what we're going to do is say that this is something along the lines of 1 plus or alpha plus beta times t times e to the minus t. Okay, so what alpha will it be? I don't know, but we can sort of transform that back into the Laplace domain, and this one, if we take its Laplace transform, will look like alpha over s plus 1. Okay, and then this one will look like beta over, well, whatever the Laplace transform of t e to the minus t is, integral from 0 to infinity of t e to the minus t e to the minus st Well, yes, by means of integration by part, we will get exactly 1 over s plus 1 squared. Okay, so what we'll see is that this guy, if I erase a little bit what I've done, the inverse Laplace transform of this guy would be something along the lines of minus t e to the minus t. Okay, now that's for minus 1 over s plus 1 squared. Now, since I'm not totally sure, I'm going to just take the Laplace transform of this, okay, and it becomes integral from 0 to infinity. I will skip the minus sign for now. T e to the minus t e to the minus st, which is integral from 0 to infinity of t e to the minus s plus 1 t, which I can integrate by part to obtain minus t divided by s plus 1 taken e to the minus s plus 1 t taken between 0 and infinity, and that is 0, and then plus 1 over s plus 1 integral from 0 to infinity of e to the minus s plus 1 t. Okay, so what we get is that this guy is indeed 0, and this guy is indeed 1 over s plus 1 squared. So this is correct. Okay, I can erase this. The inverse Laplace transform of minus 1 will be minus t e to the minus t. Okay, so summarizing and erasing everything to erasing all the unnecessary computations, what can I say? What I can say is that so I will delete this, and oops. So let me do it again. Okay. Let's try this. Oh, interesting tool. Okay. And now we can erase. Perfect. So if we go back here, okay, so we know that the response, the step response will look like 1 of t greater than 0. Okay, so the indicator is that t is equal to greater than 0 minus e to the minus t minus t e to the minus t. Okay. So what does this look like? Well, it looks like, for the most part, a exponential which does this. Okay, so the sum of so it is 1 minus e to the minus t. So that's 1 minus e to the minus t. That's an exponential that does this. Okay. Now minus t e to the minus t, it is something which does something like that. Okay. Okay, that's minus t e to the minus t. So 1 is here, and then e to the minus t is there. Okay, so what do we get in the end? Well, we get sort of the sum of these three things. Okay, so e to the minus t is like that, and so what we are interested in is sort of the response or the characteristics of this. Okay, So for that purpose, what we can do is first of all erase everything that we don't need, and then do an analysis of what happens. Okay, so let me copy again this function, okay, which when t is positive is just 1 minus e to the minus t minus t e to the minus t. I can take the derivative of this thing, and I will obtain what? I will obtain, so 1 goes to 0, minus e to the minus t becomes e to the minus t, and minus t e to the minus t becomes minus e to the minus t plus t e to the minus t. Okay, so these two terms go away, and there remains t e to the minus t. So what it means is that this is a function which never stops growing. Okay, it starts like this and never stops growing, and it goes to 1. Okay, because in limit is equal to 1, but it is monotonically increasing. And so what we will do next is study what happens. So, and remember, this is the case for zeta is equal to 1. Okay, in omega 0 squared divided by s squared plus 2 zeta omega 0 s plus omega 0 squared. Okay, now here we used the simplified variable s hat is equal to s divided by omega 0. So what we need to do now is finish by saying, since s hat, so if s hat is s divided by omega 0, our t is a t hat instead. And what do we say about t hat? But our t hat is equal to what? And I claim that t hat is equal to t times omega 0. Okay, so really the response that we have here is t hat, t hat, t hat, t hat, t hat, and therefore our response here is really not just a t term here, but it will be 1 minus e to the minus t omega 0 minus t e to the minus omega 0 t e to the minus t omega 0. Okay, so the next thing we will need to do is now look at the case where zeta is greater than 1 and zeta is less than 1, which we will see at the next lecture. Thank you.